Well, let's begin here. So today we will hopefully finish up cluster analysis. Also, we'll hopefully spend some time talking about project number 2 as well. Are there any questions before we begin? Yes?
I was looking at your video for the last time, and at the beginning of that, for the tree, you said to calculate, to find the cutting side, you shouldn't. Can you bring it?
Sure. Yep.
Sorry.
That's fine. Come on down. Like that one. Or do you want me to go to a different one?
No, the first one.
Okay, sure.
Yeah, for example, you said, I don't mean this distance. I mean this and this. But at the end, you all mentioned these distances.
Well, maybe I misspoke. But what I was going for, or at least what I should have said was, notice how this distance is not as high, or the height is not as high as this one. So you should be going between these two right here. Make the judgment. But let's say that this one was actually right here instead. Mm-hmm. Then I would be looking between this one and this one. I'm always looking at the previous joining of clusters. So in this particular case, the way that this is drawn, we have a joining between 1, 2, and 3 with 4 and 5, and then 6, 7, 8 are joined. Okay, so I should look at this and this to make the judgment. However, what I was trying to get at, I think I remember what you were talking about. Let's say that this line here, though, instead was up here, so that it was higher than this one. Yeah. Then I should be looking at this and this. Okay?
Yeah. And the distances, we actually look at the y-axis. For example, for the 6 and 8, it would be like here, and we don't care about the length.
No. Okay. No. But you're always looking at essentially where the horizontal lines are relative to the y-axis. Well, thank you for bringing that up. Are there any other questions? Okay. So most of the time today we're going to spend talking about a non-hierarchical clustering method called k-means clustering. But there's a few small things that I want to quickly go through so that we still have remaining. The first is that where we left off with the goblet data was that we have found some clusters and now we need to interpret them. The interpretation is rather easy. In fact, it often applies a lot of the same stuff that we've done before if we're using principal component analysis to help us interpret. But with the goblet data, if we had 3 clusters, we could simply look at in this case, a parallel coordinates plot. And we can see, for example, the red cluster. Well, let me back up a second here. So W1, W2, remember those are measurements regarding the cup part of the goblet. 4, 5, and 6 are essentially the bottom or the base part of the goblet. And so we can see here with the red cluster, it seems like they're just large overall, all the variables. So my interpretation for the red cluster would be, I guess I did it with respect to, at least in the notes, I did it with respect to principal component analysis. But if I were just to use this plot alone, I would say simply these goblets are large overall. The green goblets have a large top, but a small base. And so I would use that kind of a way of interpreting what a cluster represents. Now, I can also use principal component analysis, especially if I had more variables in this. I can use principal component analysis also to make this judgment. Where's my plot? There we go. Oh, no. Okay, this is 3 clusters. And so we know with principal component number 1, this is for if you look at the corresponding coefficients in principal component number one, basically the larger principal component number one is, the larger the corresponding goblet is. And so we see, again, the red cluster with 4 observations, 4, 5, and 17, seem to be large overall goblets in comparison to the rest. So that's how I would interpret that particular goblet. And then I could go to principal, then I could go to the green, the green cluster, which is for 23 and 24, and we can see that it has a large principal component number 2 relative to all the other goblets. And so I would use that to help me interpret then what that corresponding cluster represents. So you get the clusters, then you need to, of course, interpret the clusters. Sure.
Also, you mentioned for the left graph, you said as long as we know, we know the 2 PCs will show about 80-something% of variety of data, and it is clear. I don't understand how it is.
Well, it's not clear in the plot itself. You would need to actually go back to the, like the principal component analysis section, where we saw that was 85% or something like that.
Yeah. So I thought by looking at the plot, you can understand.
You cannot understand how much information that the principal components are representing of the entire data itself. You can't from this plot. You would have to look at like the proportion of variation that's, in the print comp output.
Sometimes they put the percentage at the instead of saying PC1, they put the percentage.
Yeah, it's a label.
I have never seen that label like that. I assume is that in R or some other software package? Excuse me?
In some published papers.
Okay. Yeah, that seems like a reasonable thing to do. I've never actually seen that though before. So yeah, that's interesting. Good idea. Yeah. So just to make sure everyone heard that, in a principal component score plot like this, why don't you just, in your x-axis label, your y-axis label, actually put in the percentage of the variability that the principal component actually explains. I think that would be a good addition. Okay. Now, with this particular data set, you could use the unstandardized data as well. On your own, you can take a look at my comments about it if you were to do that. There are other ways to determine the number of clusters when you use a hierarchical clustering method. This description here is for, I guess, the main other way that I've seen, and it's more of an older way to do it. And I almost took this little part, it's like a page and a half of notes. I almost took it out. I actually, a long time ago, actually taught this method. But I rarely see nowadays anybody really using this here. And like I said, I almost took it out. In the end, when I was revising my notes during the summer, I said, okay, I'm just going to leave it in. And, as a way that if a student's reading a paper and by chance they're using this particular method, here's a little bit of reference. It helps explain what they're doing. So you are not responsible for this for any of our tests or projects or anything like that. Now, before we actually talk about non-hierarchical, there's one last thing. I want to talk about something called reversals. I briefly mentioned this before. And this can happen with the centroid method. And to help motivate this, let me actually make this a little bit bigger. Imagine that we just have 3 observations. We have 2 variables, x1, and we have x2. Now, I've specifically tried to draw these 3 observations in a particular way so that you would see that the distance between 1 and 2, 1 and 3, and 2 and 3 are all about the same. But it looks like, hopefully, if I drew this right, the distance between 1 and 2 looks a little bit smaller. And so in a hierarchical clustering method, then these points would be joined first to a cluster. Now, what the centroid method says, in order to join what will, of course, be the 1-2 cluster with the 3 cluster, to find that distance, is that I need to find the mean between 1 and 2. And that distance between that mean and 3 is the next distance that I have. Now, notice the distance between 1 and 3 and 2 and 3 is larger than the distance between 3 and that plus sign there. Also, I tried to draw it this way. Maybe I didn't quite do it right. But the distance between 3 and that plus sign is a little bit smaller than the distance between 1 and 2. At least that was my intent. So notice now, in this next step of the hierarchical clustering process, the distance for that next set of cluster, for the next cluster that's going to be formed, is smaller than what it was for the previous joining. That's what's called a reversal. It's not something to be alarmed about, but it's just kind of an odd thing to think about that, as I go in the hierarchical clustering process, my distances can actually get smaller. Now, where students first see this and they think, oh, is there something wrong, is when they look at a hierarchical tree diagram, such as this. So I just found this example on a website. And so people are using R for this. And so in this tree diagram, notice observation 4 and 10 were joined, and 3 was joined with 4 and 10, and so on. But look at what happens up here. So 5 and 7 are joined in a height of about 0.38, 0.39. Then 5 and 7 is joined with what looks to be maybe observation 6. Look what happens. The line goes down. This is how so meaning the distance is smaller than what we just had between 5 and 7. This is an example of a reversal illustrated with a hierarchical tree diagram. This isn't something to be alarmed about, but this is what can happen with the centroid method and some other methods that we haven't talked about. Any questions about that? Okay. I think now, yep. That takes us then to this new material, or this k-means clustering material. So there's hierarchical clustering, there's non-hierarchical clustering, and then there's model-based clustering. We're not going to talk about model-based. We just finished hierarchical. Now we're going to talk about non-hierarchical. And we're going to focus on only one way to do non-hierarchical, which is by far the one that I see that's most used, called k-means clustering. The k corresponds to the number of clusters of interest. Now, there are both advantages and disadvantages with this particular method. First of all, in order to actually implement it, to actually see what observations are in what clusters, you need to actually specify beforehand how many clusters you want. So I need to specify I want k equal 5 or k equal 3 or something like that. And as you can and compare that to what we had with the hierarchical clustering method, we went into it without necessarily knowing how many clusters that we want or that there should be. But here we have to specify it beforehand. You might think that is a fatal flaw with this method. In the end, it's not as bad as it sounds. We will have ways to determine, well, is k equal 4 better than k equal 5? We will talk about that later. Now, a possible advantage with this method is with hierarchical clustering, we needed to actually find all distances between observations in order to actually implement it, like for a furthest neighbor or nearest neighbor. And if you have a large data set, that can be a lot. So let's say if I have 1,000 observations, How many distances are there? Well, I can use a combination, like what you see, for example, with the binomial distribution. And it would be 1,000 choose 2. And so there would be about 500,000 different distances that I would need. But let's say if I have 1 million observations, I want to implement one of those hierarchical clustering methods. Then it will be 1 million choose 2, and now you have about 500 billion different distances that you need to have. That's a lot. And so it can take a lot of time then to implement one of those methods if you're to use hierarchical clustering. But with k-means clustering, actually you don't need to find all pairwise different distances. You can actually get away with a lot less. And you'll see why shortly. So k-means clustering then can be useful to use when you have large data. I mean, you can use it with small data sets as well. So this is how k-means clustering works. So again, you're specifying the number of clusters you want to begin with. So maybe k is equal to 5. Or actually, I think in this example, k is going to be 3. Specify that you want 3 clusters. Then, let me see how I wrote this up. Then randomly choose, let's say, 3 observations from your data set. And we're going to think of these 3 observations that we choose as the center of the clusters that I'm going to start forming. These center points are referred to as seeds because you're essentially growing the cluster from that observation that you just chose. So you randomly in your data set, just let's say choose k, or in our case here, 3 different observations. So for example, this is what we could have. Typically with, again, k-means clustering, you're always going to start with standardized data. Like with the goblet data, though, there might be justification for not doing that. But you're typically going to have standardized data. So let's say I have just 2 variables to make this simple. So I have Z1, and then I also have Z2. The blue dots there are actual observations, as is the red like stars. Those are observations too, but those are ones that I've randomly chosen to be my seeds. Again, that's where I'm going to grow my clusters from. Then for each observation, assign it to a cluster with the nearest seed. So again, I can use the standardized Euclidean distance to measure the distance from each of the seeds to the other observations, and then put that observation in a cluster that is closest to that seed. So this is what I get. Again, I have 3 clusters. And so, for example, we can see that indeed this observation here is closest to that seed. So that's why I assigned it to that particular cluster. Okay. Next, we find new seeds. In other words, maybe this is not a good use of the term seeds, but basically what we're going to do is now find a new center for each of the clusters. In other words, find the means for each cluster. And so we can see, for example, for the blue cluster here, now obviously, since there's only 2 observations, it looks like the mean is somewhere right around there. And so indeed, that's where I labeled it. And so now that's the new center for that cluster. Now that I have this new center, maybe some of these observations are closer to one of these closer to these pluses from another cluster than the cluster that they were in. So now I look at the distances again between each observation and the new seeds, the cluster centers. I find all those observations and then I reassign observations, if needed, to a new cluster. And in this particular case, the way I drew it was that indeed there was one observation that was reassigned to a new cluster. Or I'm sorry, reassign to a different cluster, I should say. So next what I would do is find the centers of the clusters again by finding the means of all observations in the clusters. So now, as you might expect, this plus sign here is going to be probably moved to about there. This plus sign might be moved to there. And then I find all the distances between the observations and the cluster centers. And I look to see, do I need to reassign the observations? And I keep on doing this process over and over and over again until I get to a point where nothing's reassigned, or maybe I have, let's say, an upper limit for the number of times I'm going to actually do this iterative process. This is k-means clustering. Okay. So, some notes. I just talked about this one. It's an iterative process. Another way that you can think of what k-means clustering does, and do note that there's going to be a few places where I typed some stuff in red. It's just when I was going over my notes yesterday, I thought, it would be helpful to have this additional explanation. And so another way to think about what this process is doing is trying to minimize what you can think of it as the within cluster sums of squares. So for those of you who've had like a Stat 801 course, you've talked about an analysis of variance. There's a lot of discussion about sums of squares in those discussions. In 801 like course, you're going to see some similarities from that to what we're going to be talking about here. And so I'm trying to minimize the within cluster sums of squares. What that means is that I'm looking for a way so I can organize all these clusters so that within each of these clusters, if I were to take the observation, the numerical value, for each of the variables, subtract off the corresponding mean for that variable, square it, and then add up all those sums of squares. The sums of squares will be the smallest for whatever configuration I end up with. So here's the actual expression. I wrote it in terms of non-standardized data, but again, you could do it in terms of standardized data as well. Here's my observation, the actual numerical value. So x sub r stands for the rth observation. I corresponds to the ith variable. Remember, I have p possible variables in our general notational context. And then little k there represents a particular cluster number. I'm going to have up to capital K different clusters. What I'm going to do is I'm going to subtract off the mean, so that's why I have a bar on top of the x, for the ith variable in the kth cluster. I'm trying to minimize this numerical quantity here, the sums of squares. So again, it's called the within cluster sums of squares because notice we're comparing the observation to its actual cluster mean. So I'm within the cluster. Now, this algorithm is actually not guaranteed to find this overall minimum. Well, why is that? Why do you think? Excuse me? Well, yeah, it could find a local minimum. Yes. So it could find a local minimum. But why? Why can't it find the overall always?
Depends on the initial.
Yeah, exactly. It depends upon where you're starting. These seeds are randomly chosen. And because of that, it might not find this overall minimum. And in fact, from running it one time to running it the next time, you could get different answers. So whenever you run k-means clustering, it's good to run it multiple times and compare your results. What would you compare? Well, do the clusters make sense? We've talked about how, we could do maybe like a scatter plot of the parallel, scatter plot of the principal component scores. And look, does it make sense? There's also going to be some other ways to make that judgment too. I guess I do have this in the next. This procedure is dependent upon what observations are chosen. Which observations are chosen for seeds? Now, there's a number of different small changes to the algorithm that I presented to you that some software packages will implement in a way to do stuff faster, or maybe what they might think is better. Some of these are really small, and it's not really worth getting into all the details, but I do want to mention one here. So, let's see here. So, and let's see, in step 3 here, I found the new cluster centers, okay? And then, if you think about how a computer is going to do this, as long as you're not using parallel processing, you're going to go to observation 1. You're going to find the distance between observation 1 and cluster 1, 2, and 3 in terms of the cluster means. And you're going to see, well, which cluster mean is it closest to, and then assign that observation to that particular cluster. But let's say for observation 1, it actually gets reassigned. Then what some implementations of k-means clustering will do is that they'll say, okay, let's now immediately find the new cluster means. And now go to observation 2, find the distance that observation 2 is from the cluster means, and continue in that manner. So instead of, let's say, the way that I was trying to present it here was, and once I found these cluster means, then for all these observations, I'm going to find the distance between these particular cluster means with the observations. Then make the decision about reassignment. Instead, what you could do is that once something gets reassigned, even though you haven't gone through all the observations, immediately find the new cluster means. So just a small little thing. There's other ways to measure the center of the clusters. So, for example, you could work with medians instead. We're just going to work with means. Okay, so to see how this works, let's go back to this very small data set where we had 4 observations. Here's the distances that we have between all these observations. Now, in the end, we're not going to actually be using these distances, though. But I just decided just to reproduce the same diagram that we had before here. So let's talk about what would happen if I use k-means clustering with this data, where k is going to be 2. So to actually implement k-means clustering in R, it's fairly easy. I can use the k-means function. I put in my data. Notice that this is not standardized data. Normally, I would use standardized data here, so I would need to use the scale function with the data. Just to make things simple, I didn't do that. Centers equals 2. That's our capital K. You notice what I do right before this. I set a seed number so that I can always reproduce the exact same results. I put the results from k-means into an object called clust.toMeans for the lack of a better name. And this is what R gives us. So it gives you information about what happens at the very end of the process. It doesn't give you like iteration by iteration by iteration. And it's found 2 clusters, which is labeled as 1 and 2. So the first cluster has a mean of 5 and 2.5. So if I come up here, here's 5, here's 2.5. So right here, well, actually let's do a plus. And I will tell you that the other cluster ends up being right here. And so that what ends up happening, if you look, as I'll show you in the output very shortly, these are the clusters that are formed. The clustering vector. What that corresponds to is that observation 1 is in cluster 2, observation 2 is in cluster 2, observation 3 is in cluster 1, observation 4 is in cluster 1. Now, just note that R could have very easily called cluster 2 cluster 1 and vice versa. It doesn't matter what that number is, just what observations are which are with whatever other observations. So don't get hung up on, oh, cluster 2 was this, but now when I rerun it, it's now called cluster 1. Is there a question? R randomly chooses an observation for the seed, for where to grow the clusters from. Excuse me? Yeah, that's a good question. I do not know, but to some respect, I don't know of a good example where you would want to do that, because that would bias your results, obviously. So maybe there is a particular situation, but I can't think of one off the top of my head. So also we have the within cluster sums of squares. So for that first cluster is 2.5. Well, what does that mean? So this is cluster 1. This is cluster 2. So we can see the mean for variable 1 is 5. The actual observation for observation number 4 has a variable 1 value of 4. Yeah. So 4 minus 5 squared plus, so look at observation 3, 6 minus 5 squared. And then 1 keeps on going now to variable number 2, which is at 2.5. So I would take 2 minus 2.5 squared plus 3 minus 2.5 squared. That is my within cluster sums of squares for cluster 1. I can do the same thing for cluster 2. So for cluster 1, the value is 2.5. For cluster 2, the value is 3.28. If you add those up, you get, of course, then 7.78. And that was the overall within sums of squares measure that I showed you a few minutes ago in terms of that equation. Then we also have something called total sums of squares. What does that represent? Now, find the mean overall for all the observations for variable 1 and for variable 2. Did I actually end up calculating that and showing it? Yeah, maybe not. That's okay. Let's say that the overall mean was like, let's say, right about here. So what's going to happen for observation 1, you're going to take 2 minus its overall mean, which may be 4, plus, then you go to observation 2, you take 4 minus that overall mean, square it, and you keep on going for all the observations, for all the variables. That's the total sums of squares. And what R then presents to you is this. The between sums of squares, 7.78, divided by whatever the total sums of squares is, you get 54%. Now you might be thinking, oh, this is kind of like an R squared. that you would have for regression analysis. No, it's not. Okay? We actually want this number to be small, unlike what you would have for a coefficient determination, R squared, in regression analysis. We'll come back to this number some more later, but since we're at this place in the output, that's why I want to give you some feel for what this number is representing. Then we have some information in this output that says, okay, what's actually stored inside of the object that I calculated, this clus.2.means. Of course, you could do exactly the same thing with the names function as well. And so what this is going to be helpful for us to use for is that, let's say I actually want to extract out what cluster each observation's in. So I can go to the cluster component of this return list, and then I can use a data frame function to simply put my observations with their corresponding cluster number. This is going to be helpful for plots when we want to do plots of the data and see what clusters every observation fell into. Yeah.
I couldn't follow you. I didn't understand what is the. I mean, on the part that cluster means the variable 1 and variable 2. I noticed that it's like variable 1 is like our x-axis and variable 2 is our y-axis.
Yes.
And then, yeah, it's just this. And then when you're calculating that sum of squares by clusters, the red things that you wrote there, you did like 4 minus 5. No, the bottom.
Right here?
Yeah, 4 minus 1, and then 6 minus 5. Yeah.
So that was for the within cluster sums of squares, where what I had written out was only for that particular cluster.
Oh, it's only for this one.
For that particular cluster, yes. And then I would need to do the same thing over here. And then simply add what I get here to what I get there. And so that's what's represented. Oops, that's not what I want. So this 2.5 there is this, from doing that math. If I were to do the math for the other cluster, I would get 3.28. So that then the total within sums of squares by cluster is 7.78. And that is going to be the numerator that's going to lead to that 0.544.
What was the
The within sums of squares by cluster. So just to make sure that this is clear, that within sums of squares by cluster is this quantity.
No, I mean, you divided that by what?
Okay. Are we clear about the within sums of squares?
Yeah.
Okay. So in the end, for the total sums of squares, which I didn't write out the equation, and I will very shortly here, what you can do is look at observation 1. And I don't know what fortunately I didn't actually calculate. I don't remember what the actual mean is for variable 1, but it's probably going to be something like 4. It's going to be probably right about here, right? So I would take 2 minus 4 plus 4 minus 4 plus then we go over to observation 3 6 minus 4. And then observation 4 is 4 minus 4 squared. Then I do the same thing for variable 2. And that's going to be my total sums of squares. And so it's two measures of variability there. The actual equation for the total sums of squares would be this. Let me do some erasing. So if you're familiar with ANOVA, there's something called total sums of squares there. It's exactly the same. So the total, I'll call it TSS for the lack of a better way to put it, would be this. That would be the total sums of squares. So the x bar I represents the mean for variable I, where I don't care what cluster we're talking about. I don't care about which cluster I'm talking about. Okay, let's move on unless there's more questions. I guess I got ahead of myself before from what I was doing there. So here's a plot that actually shows where those means are. That kind of gives you some explanation for how the within cluster sums of squares is actually calculated. Now, I actually go through the process in R, showing how these calculations are actually, you could say, done. In the notes, I have this here. Note that there was a small change R about 2 years ago. Change what the argument would be for this function called aggregate. I had formula there in the notes. It's actually now called X. I am shocked that R did that, but it didn't make a change like that. Then when I was going over this yesterday, I thought, it's not even worthwhile to go through aggregate. How about we just actually write out instead what the actual expressions would be rather than use this function called aggregate. And so what we can see here, what I'm doing is I'm taking observations 1 and 2, variable 1, out of set 1, which contains my data. Remember, observations 1 and 2 are in a particular cluster together. And then I find the mean of observations 1 and 2, variable 1. I square it, that entire quantity there. And then I go to variable 2. I do the same thing. I square it. I sum up. There's where I get my 3.28 that we saw right there. I do the same thing to get 2.5. And I'm just going through some of the process of how these calculations are done. Okay. And I can get my total sums of squares is 12.67. I can extract that out from the object that was returned. And actually, I go through the details of programming in the formula that we just talked about with respect to calculating the total sums of squares, and I get 12.67. So when we take, let's see here. Yeah. So when we take, let's see here. I apologize. I actually misspoke earlier. Okay. I should cut that. I'm sorry. So notice, let me actually do some erasing since I've written over it too much. Notice it says between sums of squares, total sums of squares there. That total sums of squares was that 12 point, let me just get the right number, 12.67. this between sums of squares is different from the within. So again, in ANOVA, you often have within treatment sums of squares. That's equivalent to within cluster sums of squares. You'll have total sums of squares, and then you have sums of squares. What's the word? Well, I'm sorry. The SSE, sums of squares error, is essentially what within cluster sums of squares is. Okay. Let me actually write out. So, like sums of squares due to error in ANOVA. Like total sums of squares in ANOVA. And then if you remember, if you took in ANOVA TSS minus SSE, you get what some people will call SSTR, sums of squares due to treatment. That's what this between sums of squares is doing. And all it is the difference between the TSS and the SSE, or total sums of squares from the cluster minus the within cluster sums of squares. That's where we get this 54%. I'm sorry. I think I was just getting ahead of myself explaining some of this when I had it correctly outlined in the notes. And so I give the details about what this value represents. Okay, so what would happen if I changed the seed number? Well, let's say I changed to 7813. So when I use set.seed, suppose I use a different number in that. This may cause R to choose different seeds to start the clusters from. And in this particular case, that is true. And so now, observation 1 is in cluster 1. Observation 2 is in cluster 2. Observation 3 is in cluster 2. And observation 4 is in cluster 1. So observations 1 and 4 are together. Observations 2 and 3 are now together. Of course, and that means I have different final cluster means. Okay. So that gives you a little bit of an idea of how k-means clustering works and some of the actual R code that's involved with it. Now let's talk about how we can get around that issue about, well, I have to actually specify capital K to begin with. Sure. Yeah.
I mean, if our data set was not like this, because it's like, I mean, it's not clear that really which two are clusters. But if it was, I mean, obvious, and then we choose different seeds, we would get different clusters.
Not necessarily. And you know, I put together this data set on purpose to make sure to emphasize you can get different clusters, and also it's a very simple data set. But you know, let's say if I have something like this. So I have just two variables, and this is where the points are. If I choose a different seed number with k-means, I'm not going to get different clusters.
Yeah, so because I don't remember exactly, but I was doing that k-means clustering with SciPy in Python for my data set, and I mean, obviously I got like the same results each time.
You know, I suppose there is let's say a non-zero chance to get different clusters in this setting. You know, let's say I choose this as my seed and I choose this as my seed. Okay. I could see that the clustering algorithm may never ever get over here for a new cluster mean. I could see that happening. I think it would be rare, but I could see that happening. The key is repeat the process. Don't just go with your first run. Okay, so how do I determine the number of clusters? Well, we talked about how, for example, we could do some kind of scatter plot of our data. We could do a parallel coordinates plot of our data, or do the scatter plot, parallel coordinates plots of our principal component scores, and see what makes sense. Does k equal 3 make sense? Does k equal 5 make sense? But here's a numerical way to make a judgment about what you should use for k. And that is this. We form this ratio, and this is why I unfortunately made the error earlier. This ratio, we're just going to call it W for the lack of a better letter. We're going to take the within sums of squares divided by the total sums of squares. We're going to use that as a measure to compare, let's say, k equal 3 to k equal 4 to k equal 5. Let's see here. So I want us to think about here, do we want this number to be small or do we want it to be large? That's right. Thank you. We do want it to be small. And let's just think of it in terms of just a fixed k for now. Maybe I chose k equal 3. Why do I want it to be small? Let's come over to these additional plots that I drew out. So I have two different scenarios. We'll call this, let's say, case A. We'll call this case B. And the way that I tried to draw these plots was that the observations are essentially located relative to each other in terms of within the same cluster, basically the same distance in both plots. And we would hope that any kind of clustering algorithm, let's not talk about that one yet. We would hope that any kind of clustering algorithm would conclude like what A did there. Now, in this scenario, I want you to tell me which is going to have a smaller W. Is it A? Or is it going to be B? A. A. Now, the way that I try to do this is that, or draw this, is that within sums of squares is always going to be the same. The total sums of squares is what's going to differ. So the smaller the W it is, the better. Now, would you like to conclude what B did there? Is that if you had a choice, let's say, between A or B, in terms of you want to have data where it's completely clear what clusters observations should fall in, would you prefer to have A or B? A. Okay? Because it's quite separated. B, if I didn't have, let's see if I can draw this. If you just look at it like that, is it obvious where I had those blue circles before? No, it's not. And so we are hoping for situations like A. And you can see how this W measure kind of tells us that information. Okay. So the way that we're going to use this W measure is as follows. We're going to choose, let's say, k equal 2, calculate W. Choose k equal 3, calculate W. And we're going to keep on doing it up to some upper limit for whatever we think k should be. Maybe 20 or whatever. There's not necessarily always one right answer. And then we're going to do a plot like this. It kind of looks like a scree plot, if you remember from principal component analysis. And we're going to actually kind of interpret it that way. Where what we're looking for is where, let me this out. What we're looking for is where the plot starts to level off. So on the y-axis, the x-axis I have k, the y-axis I have this measure w. And you can imagine that as you add more and more and more clusters, that within sums of squares, it's probably going to get smaller and smaller and smaller. Total sums of squares isn't going to change. But as you add more and more clusters, the within sums of squares is going to get smaller and smaller and smaller. Think of a situation where you have, capital N different observations, and you set k to be n. What's the within sums of squares? 0. And where is the within sums of squares going to be the largest? Well, when k is equal to 1. In fact, it's going to be exactly the same as the total sums of squares. And so we're looking for, it's almost like the whole thing about eventually, like the law of diminishing returns. I could keep on adding more and more clusters. I could get my W smaller and smaller and smaller. But at some point, is that little bit that I'm gaining by adding, let's say, one more cluster, is it really worthwhile? And so that's how you interpret one of these plots. You're looking for a point where essentially we have a leveling off. And in this particular case, right about 4 seems like. With k being more than 4, I'm not gaining much. And so from looking at this plot, I would say, okay, I think k equals 4 is the best. And then I would say that's what I'm going to use for my number of clusters. Again, let me emphasize though, I would still look at some kind of scatter plot. I would still look at some kind of parallel coordinates plot as well. So what I would do is when I see k equal 4 there, I say, okay, let's now draw a parallel coordinates plot. Let's draw a scatter plot of the principal component scores or whatever I'm plotting. Let's look at one of those plots. Does k equal 4 make sense? If it does, I probably stop and say, yes, I'm fine with k equal 4. If it doesn't make sense, then I might start looking at, okay, well, let's see what happens if I get k equal 5. Or, maybe the plot might suggest to me, oh, I can go down to k equal 3. Or I should go up to k equal 5. That's how then I make a final decision about how many clusters I should choose. Okay. So we talked about if I use different initial cluster seeds, I can get different results. And we also talked about how you should rerun your k-means clustering algorithm multiple times to make a judgment of to decide, well, are things changing, and what are these new clusters? So, what should you actually do in practice here? Well, what I would do is, again, just simply run k-means with a few different values in my set.c. Look to see if things are changing a lot. I may actually, I use that W to help me choose an initial set of clusters. Let's say if I ran this procedure 3 or 5 times, I might look at plots all 3 or 5 times. Alternatively, what I might do too is look at that W for the 3 or 5 times I'm running this k-means clustering algorithm. And then let's say on one of those, let's just say I have 5 different runs. One of those 5 different runs, I have the smallest W of all of them. I might just focus on that. And then do my plots. Another way to do this is as follows. There's an argument called nStart in k-means. And this will essentially allow you to implement the k-means process as many times as you put in the nStart. Where it will simply, randomly select seeds the first time, run k-means. Randomly select seeds the second time, run k-means. Do this 10 times, and then the results that are returned to you are the results that give you the smallest w. And so it's kind of an automated process, the way I described to you a minute ago. The one problem with this is that you don't actually get to see all the other runs of the k-means algorithm. And that might be of interest just for comparison purposes to see, well, this W is, let's say, 0.5, and this W is 0.5000001. Well, maybe that 0.50001 case gives you clusters that make a little bit more sense than the case that you had with 4.5. And so that's what you're missing out on, though. Let's see here. Okay, so let's go to the goblet data. So I'm going to use the standardized data. I'm going to use capital K equal 1 to 10, and I'm going to run 10 separate runs for each capital K. So to run this over the different possible values of K, we actually have to do some programming to get this done. And so I'm going to write a for loop to help me out here. Okay, let me just read some stuff in. I actually had this all ready to go, and then I had to reboot my computer, unfortunately. And I forgot to reread the data in. Let's make sure that this did all this. Okay. So to begin with here, I'm going to specify my levels of K, capital K. And then I want to be able to save my within sums of squares from each run. My total sums of squares isn't going to change because it's the same data. But my within sums of squares could change because I have different clusters. And so to save my within sums of squares, what I do is I create basically a vector as a place that I'm going to save the results in when I do K equal 1, when I do K equal 2, K equal 3. And so the way to do that is I'm going to use a function called numeric. And I can specify within inside of numeric how long it should be in terms of my vector. So if I say numeric 10, look what I get. I get 10 different zeros. Instead, I just said the length of k dot levels. And so this is going to be a vector, then I'm going to replace the 0 with what I get for k equal 1. I'm going to replace this 0 with what I get for k equal 2, and so on when I do my for loop. I set a C before I begin my for loop so I can reproduce my results. And then I say for k, capital K, in my k levels, do the following that's within these curly brackets. I run my k-means function with my standardized data. And do I have my standardized data? Yes, I do. So my standardized data is in an object called Z. What my value of k is, and then I say n star equal 10. So for each k, it's going to run it 10 different times and going to return the result to me from the best W. I put the results into clus.means, and then I take that within sums of squares out of clus.means. I sum it. Remember what we saw for that simple example where we had 4 observations. I had cluster 1 and I had cluster 2's within sums of squares. And so I'm just going to add them together, put that into the kth element of save.wss. And so that if I look at this, well, I could run it and then look at save.wss. Those are all my values. Okay. I can extract my total sums of squares from, it doesn't matter, whatever I had last run for my k-means function. And then if I say save.wss divided by total sums of squares, we have information. Oops. That's a little bit of an error in the code. That should be k.levels. Doesn't affect anything. Everything else is correct. And so there's all my k values and that w. Let's do a plot. K levels on the x-axis, my w on the y-axis. And there we go. So from that, I want to choose what capital K should be. Let me jump back over here to my notes. And so what I'm looking here is for where does the leveling off start? In the notes, I say about 5. When I was going over my material for yesterday, I immediately went to 4. This kind of shows you that you can have more than one choice. But definitely I wouldn't choose 1, I wouldn't choose 2, I wouldn't choose 3. I would say probably 4 or 5. But this also allows you to say, well, maybe I should take a look at what 4 and 5 looks like. Maybe I should even take a look at 6. Do I get much benefit from 6 when I look at like a principal component score plot? When I look at a parallel cornice plot of my original data or my standardized data. So let's take a look at what happens though when we do work with 5 clusters. Now, here I am not guaranteed to get exactly the same 5 clusters that I got from that for loop. But since I'm using n star equal 10, I'm hoping that I should get about the same. If one wanted to, one could compare the W from running it here versus the W that you got in the output from the for loop. If there was a considerable difference, then I would say, wait a second, what's going on here? I would want to maybe even rerun it again with a different initial seed. So I say set.seed. I use my k-means function. Centers equal 5, n star equal 10. Here's what I get. So notice what R does. It actually prints off the means for each of the clusters. The clustering vector again tells you what observations are in which cluster. So observation 1 is in cluster 4. Observation 2 is in cluster 2. Now, let's say you had a very large data set. Would you want to actually print off this? Probably not, because you're going to have all this information being there. You know, if you have 1 million observations, you're going to have 1 million numbers. So that's why it's always good. You know, we're saving the results to here, and then I can extract out then what I need from that returned object. We have some information about within sums of squares of clusters, that between sums of squares divided by total sums of squares, and so on. Now, because we're running a little bit short on time, we're going to focus on the output here rather than going through this function. So I wrote a function that you'll be able to actually use yourself on the project called pca.ca.plot2. It kind of similar to what we saw for the hierarchical clustering, where what happens is that you can pass some information into it, like the results from this k-means clustering, and it's automatically going to do principal component analysis for you, where it's going to do a plot, 2-dimensional plots. It's going to do 3-dimensional plots so that you can make sense of the clustering results. And so when I have 5 clusters here, this is what I get. Well, now I can't erase. Oh well. So I have a cluster here. I have a cluster here. I have a cluster here. Oops. Come on, let me erase. Those are my 5 clusters. Some of them definitely make sense. Others maybe I'm a little bit concerned about. In particular, these right there. maybe that one as well. And so this then allows you to say, okay, well, maybe that 5 that I chose, maybe I should have went to 4 instead, and see what that gave me. Now, we do have some information here about, well, why is 5 being chosen? Notice, this, the big clump of points that we have here. Notice it's that principal component number 3 that seems to be making some of that judgment for us. Let me actually run this. So here's my function, pca.ca.plot2. And so what I do is I pass in my data, my cluster results, and also I put in a title. So let's take a look at the 3D plot. So we can see, again, the green and the black definitely stand out from the rest there. It's just questionable about the red and the blue. I guess the 2 different colors of blue as well. And we can see maybe some differences there, but maybe not enough to really to make that judgment. I could see that these, if you see where my mouse is, where these light blues could be separated from the other ones as well, but it's questionable the red and the blue there. Oof, that's a mess. You could also do a parallel coordinates plot to see this as well. And we can see again the black and the green definitely stand out from the rest. The blues and the red is not quite as clear. Maybe the lighter blue. Maybe there's some justification for that to be different from the rest from this particular plot, but definitely the darker blue and the red, it's quite questionable. And so these are the kinds of judgments that you will need to make for your project with respect to your own data. So let's take a look at project number 2 again here. So problem number 2 of the cluster analysis, what you're going to do is perform k-means clustering with the standardized data values. Make sure you set C numbers in your code so that I can reproduce your exact results. That's going to be very, very important. So part A then says, okay, let's determine an appropriate number of clusters using the W statistic. So in other words, you're going to adapt that for loop code that I showed you. You're going to do one of those plots of the W's versus the K and make a judgment about from that for what would be an appropriate value of K. Then construct a scatter plot of the first 2 PCs. Include the cluster memberships in an appropriate manner on the plot. Comment on how well this plot helps to justify the clusters. So the very first principal component score plot that I showed you. You're welcome to do the bubble plot. You're welcome to do the 3D plot as well, the principal component scores. You can use my function. But at the very least, I want to see the scatter plot of the first 2 PCs and use you and assume that these, and you can make a judgment about, well, are these 2 PCs giving us enough information about my data that I feel comfortable that it's showing me everything that I need to know. But assuming that it does, then interpret that plot in a correct manner. Do those clusters make sense? Then do also a parallel coordinates plot of the data, not the PCs, but the standardized data values themselves. Again, standardized data. Include the cluster memberships in an appropriate manner on the plot. Comment on how well this plot helps to justify the clusters. Then number 3 here is I want you to make comparisons between what you had for using the hierarchical clustering method in 1 and the k-means clustering method in 2. And I want you to do a table such as this. Let's say that we'll call this hierarchical. We'll call this k-means. And both ended up choosing 3 clusters. That may not happen to you. But let's say that it chose 3. And let's say I had something like this, where I I put in the table the number of observations that fall in each cluster. And I got something like this. Do your clusters agree? Are the results the same between the 2 clustering methods? Yes or no? Yes. Okay. Let's say instead I had something that looked like this. Do the clustering methods agree on the clusters? Yes or no? The answer is still yes. Why? R just chooses to call maybe these observations cluster 1, these observations to be cluster 2, these observations to be cluster 3. But then when you use another method, it could be exactly the same clusters, same observations, the same cluster. It's just a different labeling. So in this particular case, the clusters completely agree. Now let's say I have something like this instead. Do the clustering methods agree? No. Okay? But it will be interesting to compare your results from one clustering method to the other. Especially, let's say maybe you chose 4 clusters. How does this all work out? Maybe I have this. And so what, in this particular case, to interpret this, we can see, okay, what k-means clustering calls cluster number 3, for some reason the hierarchical method splits into 2 different clusters. That's what I want you to do. By doing a contingency table like this, there's a number of different ways to do contingency tables in R. There's, for example, the xtabs function. There's a table function as well that would work. And that can be very helpful to you. Look at the help to learn further about how to use that function. That can be helpful to you to construct a table like this. Okay, sorry that we went over again for the second straight day. So what's next in our class? I have office hours today. There's a little bit left to go with cluster analysis that we'll finish up next time. And then we'll also just start a new topic next time. And then project number 2 is due Friday, November 3rd at 5 p.m. So this Friday. Are there any questions regarding our material? Okay, sorry that I went over again, but that is all for today.